Alright, so I want to do a video talking about mixtures of acids. So there's two possibilities. There's a mixture of a strong acid and a weak acid, and a weak acid and a weak acid. Now if you're wondering about the strong acid and strong acid, we've already talked about that. You just put the concentrations together and that will be your new hydronium concentration. But with a strong acid mixed with a weak acid, you have to remember that strong acids ionize completely, no matter what. So what's going to happen here, we have some formic acid and HCl together. Now, no matter what, you do have to keep in mind that there is going to be hydronium coming from the autoionization of water, but this is such a small number, typically we just don't even bother worrying about it. So we just kind of mathematically pretend like it doesn't happen. So the strong acid ionizes completely, which means before we even get into the ice table of the weak acid, like we normally would, we have hydronium. So what this means, practically speaking, is when we make the ice table for our weak acid, we're going to go ahead and plug in the concentration of the strong acid for our initial hydronium concentration. So we got HCl with this concentration. The formic acid, you also have 0.1 molar, and then you just work the ice table like normal. So you'll have the K value of the formic acid, and that'll be equal to your 0.1 plus x times x over 0.1 minus x. And then obviously you can still do the x is small and all that sort of jazz, but things turn out a little bit differently. But also, since we're dealing with weak acids, a lot of times the x is small approximation is going to make it really easy. In this case, both this x and this x go to 0. Then since you have 0.1 on top and bottom, those cancel, and then the Ka is equal to x, which makes that nice and easy. But that won't always happen. There are different scenarios. If you have two weak acids, this is where things can get a little tricky. Typically, when you got two weak acids, what you want to do is figure out which one of them is the stronger of the two acids. Figure out which one's stronger, and then the stronger one, do an ice table for it first, figure out the hydronium concentration at equilibrium, and then, like we did with the strong acid, you'll take that first equilibrium hydronium concentration and plug it in as the initial hydronium concentration for the second weak acid. That is typically what's going to happen. Now, there is a way that you can skip doing all that, and that is what I'm talking about right here in this paragraph. If the Ka values of the acids are significantly different, as in, I would say 3 powers of 10, sort of the same as your x is small approximation, 3 powers of 10, and the two acids are either equal in concentration, or the stronger of the two acids has the greater concentration, then you can go ahead and just do the ice table for the stronger of the two acids and not even bother doing the ice table for the weaker of the two. But that's the only scenario. Otherwise, you got to do an ice table for both, starting with the stronger one and then working to the weaker one. So let's take a look at this. In this case, you have two weak acids. Notice that you have 10 to the negative 4th, 10 to the negative 8th. That's 4 powers of 10. So that is a significant difference. So we want to make sure the concentrations are good. Look, the HF, which is the stronger of the two acids, has the higher concentration than the second one. So what that means is we just pretend like the second one doesn't exist, and you would just do an ice table for the 0.3 molar and call it quits at that point. So like I said, things can get a little tricky. I'll probably do another video where I do one of the harder ones, but I just wanted to talk through that a little bit. And that's all for this one.